Welcome back. So, in today's video lecture, we will discuss about the microemulsion. You will get in this video lecture, you will get a good insight into how microemulsion is thermodynamically a stable system. Okay, and you will also understand about different types of microemulsion phase at equilibrium. We will also take you to the concept called ternary phase diagram. Where you will be able to identify the location of oil water and water oil microemulsion. Finally, we will also look at the applications based on the microemulsions. Let's begin. So historically, microemulsions were first discovered by Rodward in 1928 in the form of liquid waxes. So, as such, microemulsion is used in various formulations. Uh, you know, uh, for drug delivery application, or also as products in the form of microemulsions, right? Uh, so we look at the thermodynamic concepts. So in general, microemulsion is a clear and thermodynamically stable system uh, compared to the regular emulsion system. Um, the stability is better, and it is thermodynamically favored uh, by the uh, Gibbs free energy, the change in Gibbs free energy. If you look at the equation over here, so we know that the changing Gibbs free energy equation is basically nothing but a contribution from the enthalpic as well as entropic contribution, right? So in this case, the interfacial tension is very, very low. Uh, or you can also say interfacial tension is very, very negligible. Because when you emulsify the droplets, so as we mentioned here, the typical diameter of the dispersed phases, the droplets, is typically between 10 to 100 nanometer. Okay, in such scenario, one would expect a large number of droplets generated in the system, which means that the droplets, uh, the surface area that is generated by the droplets are very, very high, or you can say um, very large, right? So in such scenario, you would expect that the enthalpy contribution is very high. So enthalpy contribution is denoted here as the product of surface tension and the change in the surface area. In this case, change in surface area is very high. Okay, and that is very well taken. But at the same time, the entropic part, if you look at, so statistic, if you go by the statistic definition of entropy, you can understand that the number of droplets that are generated plays a major role here. So because n is very, very large, entropy will be highly positive in this case. So delta G will be naturally negative in this case, because the contribution of enthalpy, although change in surface area is very large in this case, because we employ surfactant and co-surfactant, the synergistic stabilization of these two surfactants lead to reduction in the surface tension to very large extent. Okay, so we can even say that the surface tension in this case is negligibly small. So in such scenario, you would end up getting only the entropy contribution. So in this case, the delta G, which is uh, change in the Gibbs energy, is negative, and it is purely driven by entropy contribution, right? So that's why we can say that microemulsion is thermodynamically stable system, okay, than emulsion system. Uh, that is because of the application of surfactant and co-surfactant, right? Uh, so we can also look at various types of microemulsion as we uh, move along, and we will look at the phase diagram, three phase diagram of the surfactant and uh, surfactant, water, and oil, all three components. Okay. So apart from the application in drug delivery, sometime the products are also sold in the form of microemulsion. Okay. So a lot of commercially uh, so microemulsion is this technology is used nowadays in a lot of commercial segments. I mean, it's commercial products as well. So you can look at in this example which I have given here, uh, a company called Catalent, which is a healthcare company which uses omega zero technology. Okay, this is actually based on the microemulsion. So here the product is sold in the form of microemulsion, basically to encapsulate. Here the microemulsion is used to encapsulate uh, the fish oil, right? Okay, so basically it helps masking the oil smell, right? So like like how likewise microemulsion is used in the formulation, okay, especially in drug delivery application. Okay, so we will look at what are the different types of microemulsion, and we look at the phase diagram. Okay, so from phase diagram we can understand various domains. Okay, uh, so how one can choose depending on the state of emulsion, the right domain, right experimental domain, a region, or experimental operating regions based on the three phase diagram. Okay, right. So here in this section we will look at different types of microemulsion phases at equilibrium. Uh, so in the context of microemulsion, Winsor has classified four types of microemulsion phases. Okay, let's say Winsor one phase. So let's say you employ surfactant, co-surfactant, and microemulsion. In the sense, you try to stabilize oil in water emulsion, but in the process, sometime you end up getting excess oil. Okay, which is not being part of the emulsion. Okay, so in such case, you will have oil in water emulsion lying below the excess oil phase. Okay, um, like the one shown here. So in this case, the excess oil being lighter than the water component. So in the case of oil in water, water is heavier component. So that's why the emulsion phase tries to settle at the bottom, whereas the oil being a lighter component that lie above the emulsion phase. Okay, so such case such emulsion is called as Winsor one type emulsion, micro emulsion. Okay, right. So what does it indicate is the emulsion is not 100%, right? There are some portion of oil which is not converted into emulsion. Okay, so there is another type of micro emulsion. Sometimes instead of oil being excess component, you may uh, end up getting water being an excess component. In such scenario, because water is heavier component which will lie below the water in oil emulsion phase. Because in the case of water in oil emulsion phase, oil is a continuous medium. Since oil is a lighter component than the water, this entire emulsion phase will be floating. Okay, uh, uh, will be floating, and that's why it will be lying above the water phase. Okay, uh, so so this is nothing but Windsor 2 microemulsion. I mean type Windsor 2 type microemulsion. We talk about Windsor 3. So in this case, what happens is, um, so you would get uh, both oil and water as excess phase. Sometime when you deal with the emulsion, instead of getting emulsion droplets, one may uh, end up getting bicontinuous or co-continuous structure, which is basically nothing but a network structure. Okay, so so in this case, the co-continuous domains are filled with emulsifiers, right? And in such scenario, you may end up getting both water and oil as an excess component, right? Um, this type of microemulsion is called Windsor 3, and last but not least is Windsor 4. In this case, let's say you achieved 100% emulsion. Okay, so neither water was found in excess quantity nor oil was found in excess quantity. In this situation, you would say that the emulsion achieved is 100%. Okay, such type of uh, emulsion is called Windsor 4 type microemulsion. Right. In this case, you can regard this mixture as a homogeneous mixture of oil, surfactant, and water. Okay. So these are different types of microemulsion phases at equilibrium classified by Windsor. So here we will look at the ternary phase diagram. So three phase diagram of microemulsion involving surfactants, water, oil as components. Okay, for brevity, let's understand that each corner represents pure species as pure components. Let's say this corner and this corner and this corner. If you look at each corner represents 100% pure components. So in this case, you have 100% water here, and here you have 100% oil. Here you have 100% surfactants. Okay. Now, question is, um, when you blend these three components, uh, what sort of state will the system be? Will the system attain? Right. So that is what we are trying to ask. So this phase diagram will tell us which operating regime one has to choose, um, depending on the application. Okay. Let's say if I am looking for oil in water microemulsion, then which experimental operating point one should choose? Or if I am looking for water in oil microemulsion, which will be my uh, you know uh, a pathway, which will be my the domain, right? Which would be my experimental conditions. So if you want to uh, stick to some specific experimental condition, okay, to achieve some specific structure, then it is required that one should refer to the phase diagram, right? So when you balance the blend of these three components, one can achieve a desired structure, a desired state. Okay. So let's say we talk about, let us start with let's say we're talking about this zone. Let's say we have uh, sufficient, I mean, lot, the water is very present in a very large quantity. Let's say we are somewhere here, the water is present in very large quantity and oil is present in very minor quantity, right? So in such scenario, because water is continuous medium in this case, so you can expect that uh, because you can expect micelle like structure, uh, mostly uh, because we have very less quantity of oil and uh, and huge quantity of water. It is difficult to prepare an emulsion, right? System, the surfactant, the system cannot generate emulsion in this case because we have very, very smaller quantity of oil. Okay. Whereas because the water is a continuous medium, I'm talking about this region. Since water is a continuous medium, the backbone of surfactant, right, which is a hydrophobic component, would want to minimize its contact with water. So spontaneously, they will self-assemble to form a structure like this, right? If you simply place surfactant into a aqueous solution where little bit of oil is present in a very, very minor quantity, in such scenario, you would end up getting micelles. So here in this case, because you don't have a sufficient quantity of oil, you cannot expect emulsion, any type of emulsion in this case. Whereas on the other extreme, if I look at, so we're talking about this extreme, we are closer to 100% oil. Okay, uh, we are very closer to 100% oil, which means that you got very less quantity of water. Larger quantity is filled with oil. In such scenario, you would be you know most you will get reverse micelles most likely because what will happen is because you have oil which is a continuous medium in this case, the surfactant which contains head group and tail group, the head group would want to minimize its contact with oil, so they will automatically self assemble to form a structure like this, right? So this is called reverse micelles. Okay. So here also we don't expect any emulsion to be formed because you don't have a sufficient quantity of water or oil. Although you have a larger quantity of oil, but very less quantity of water is present. That's why in this region also you will not get any emulsion. So these two regions, experimental region are very clear. We know that in this region you will not achieve any emulsion. We are talking about oil water microemulsion. So if you look at this region, here you will get getting oil in water microemulsion is most likely because in this case you have sufficient quantity of oil, um, sufficient quantity of water, and sufficient quantity of water and minimal amount of oil and minimal amount of surfactant. So in this case, because water is a very continuous medium in this case, water is a continuous medium in this case, you would expect oil in water emulsion. Okay. But here, this region is mostly favorable for microemulsion. Whereas on the other hand, water in oil emulsion is most likely to if you are in this region, right? It's because here oil is a continuous medium. So 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 in this case, it will be forced system will be um, it will be system will be forced to form water in oil emulsion. Okay, if you are in between these two region, experimental region, you would get either water in oil or oil in water depending on the wettability of emulsifiers. Okay, um, so So that depends on the wettability of the surfactants. And on the other hand, you have the domain where you will get bicontinuous like structure. Okay, uh, so this structure is um, favorable. So lambda. So this bicontinuous structure is favorable when both water and oil exist in same quality. When we say same quality, what it means is that um, so the point at which the emulsifier will would want to weight both phases equally likely. Okay, in such case, uh, surfactant, the emulsifier will not choose any particular phase uh, more favorable than the other, which mean so since both are, so what is left out is the macro emulsion. So this is nothing but the regular emulsion where the droplet size is more than few tens of micron meter. So uh, this region doesn't favor, okay, micro emulsion at all, because this doesn't belong to ultra low interfacial tension zone. Okay, so micro emulsion will be favored only when we are hitting ultra low interfacial tension zone. Okay, otherwise, it will not. One would not get micro emulsion, or you can say that the emulsion droplets will not be in the size range between 10 to 100 nanometer. Okay, so this is various structures, and depending on the composition of one of these three components, one would get a desired structure or output from these three components, from these processes, right? So this will it's like a kind of guideline for us. Okay, one can easily map based on these phase diagram. So this is very useful, um, you know, in the case of when we are dealing with the formulation and things like that. When you are preparing a particular, when you want to prepare a particular product, a particular uh, you know uh, state, when you want to achieve design such a particular product, then you can you know refer to this phase diagram. So here we will look at some applications of micro emulsions. So you would find application of micro emulsions in various fields, but I think I have listed a couple of them, for a quicker understanding. Okay, the the first one that we can look at is the enhanced oil recovery. Okay, so in the field of oil exploration, one can extract oil in at least in three different stages. Okay, so in the primary and secondary stage, when we use gas and water to pump the oil out from the reservoir, we succeed, to extract to some extent. Uh, so, but this process leave about 50 to 70% of oil within the reservoir itself. Okay. So where does this oil go? The oil is this oil will be held up in the pores or the porous network channels within the reservoir itself. Uh, because the pore size is very very small, tiny, you can expect pressure drop within the pores will be very large. Okay, for instance, if we consider that the pore is structured to be a cylindrical geometry, we know from the Laplace equation, we know this delta P will be you know uh, gamma by R1. Um, so in this case, you would expect that, say, let's say R is very small. Okay, R is very small. In such case, uh, the delta P will be very, very large. Okay, typically about 300 to 500 psi also. So it is very difficult to visualize any flow condition across a pressure drop of, let's say, 300 to 500 psi. Okay, so because the capillary force is uh, will be very much dominant because of the very high surface tension force or very high surface tension value. Typically, the surface tension will be 10 to 50 millinewton per meter. So here comes the application of micro emulsion. It can be very well applied here. Let's say if you use a mixture of surfactant and co-surfactant, okay, so we can minimize the surface tension to a large extent, at least 2 order magnitude from the existing surface tension value. So in that case, you can reduce the delta P drastically. Uh, so it can be reduced to a large extent. So then it is easy to visualize the flow condition across such very, very small channels. So it can be easily, the oil can be easily extracted from the porous network structures. And so we can utilize, by utilizing the microemulsion application, uh, we can effectively remove the oil from the reservoir. The second application that we can look at is the emulsion polymerization as polymer synthesis. Usually, this polymer synthesis is in this polymer synthesis. Usually, emulsion polymerization route is uh, chosen in case the monomer that we work with is not water soluble. Okay, if you have to deal with water insoluble monomer, generally emulsion polymerization route is often chosen. Uh, so it's because it is possible to carry out such reaction in the even if uh, even if you are dealing with immiscible mixtures. Okay, so in such case, the reaction, the whole polymerization reaction, will be carried out in the droplet itself. Uh, so since the concentration of monomer that we choose is usually above CMC, you expect sometime other states, monomer, I mean, other the monomer will be present in other structures as well. For example, micelles, uh, there will be individual monomers also. Okay, and an emulsifier. So this will also be acting as an emulsifier because they will be around the droplet as well. Okay, since the reaction occur within this droplet, and since we talk about microemulsion, the droplet size will be very, very small. So we expect the polymer molecule also to be uh, about, let's say, less than 100 nanometer, or typically between 100 to 200 nanometer. So this is so in this way, the emulsion polymerization can be effectively utilized. Uh, you know, by combining the microemulsion. Okay, you know uh, concepts here. Okay, so these two are as very easy for us to relate. These two applications widely I mean, microemulsion is utilized in these two applications in a significant way. Okay, I think it is very easy to relate also, right? So we stop here. We will continue from the next lecture. Thank you.